Good morning and welcome to the latest glibc math improvements. This is something that I would like to present you because there's been a lot of new features in glibc math library and I don't see much discussions out there. So just to give a brief summary, the first part is just to give with the math support is on glibc, what kind of float type we support, what kind of standards we aim to support, the kind of architectures that we would like to support. So the next part is a bit of history. It's basically to lay out for the next one and showing what kind of work we've been doing during this almost 3 decades of the math library, and the problems that we found, things like bad designs that we need to carry on and we need to fixing over time. And it's a big, long part, but the whole idea is to have on the third part, which is lessons learned, basically what we need to avoid and what we need to focus on to improve the math library on glibc, and the kind of work that we did on the latest year to improve performance and correctness. And the fourth part is the most recent work that we've been doing. The whole idea is for the correctness and standard compliance mode on all the math library and the adjacent libraries, and how we plan to integrate new projects and new algorithms to improve both correctness and performance. And the latest part is future development, which is something that I do not have set in stone, so I would like some feedback, because there is a lot of topics that we can focus on and there is not much developers that we can work with. So if I can have some ideas and some discussion from the topics I bring, it will be really helpful. So math support on glibc. We support the latest C++ standard. Currently, I think we are finishing the C23. We do not support all the extensions, but we aim to support pretty much what the default standards defines, which includes the complex functions, float environment, the float header itself, and the math library, which is the largest one. And we do support some extensions. For instance, on x86 and ARM64, we support lib and vec. They are not really paired together. They are developed independently and with different projects, but they are supported in full. And we support different floating types defined by the C standard, which includes also new floating types that are platform independent by the new standard. And on some architectures, we also support other floating points like float.h, but it really depends on the architecture and the ABI. So under the hood, we have a lot of implementations for different floating types. We have the default one, which is the float and binary 32. We have double support. We have this double 96, which is used by some x86 and M68K support. It's a mixture between C implementations and assembly one. We have the IBM long double, which is a trick a PowerPC does for this IBI, which is a long double that is formed with 2 doubles because the hardware does not have support, at least the old hardware does not have support. We have the float.h support, which is provided in some architectures as is either long double or an extension as float.h. And we also have some implementation for the soft float implementation, which does not use floating types internally, but provide float implementations for some architectures. And we also had a lot of architecture-specific assembly code to optimize some routines. And it includes libmvec for some architectures and other stuff that we have internally, mostly for the float environment and some long double support. So right now, I think, if I recall correct, we are up to date to the C standard, meaning I think Joseph has finished the C23 math support for all the new functions that C23 defines. And we support both Arno and exceptions, meaning that our implementations are a bit more complex than what C requires. And there is a lot of symbols that libm supports, and it really depends on the ABI. So we have some, for instance, arc that only provides 800, but on the other hand, we have PowerPC 64LE, which supports like the double. PowerPC, it's kind of outlier because it supports multiple types, and it did an ABI transition, meaning that we need to support both two types for the long double, both float 128 and the old IBM long double, and it depends on how you compile your object, the type we're going to be using. So it and there is a lot of code. Oh, go ahead.
On backend and how we support double and long double as well.
Yeah, there is another one which it's another ABI. So PowerPC, it's like 3 different floating ABIs that we currently support. But the newest one is they try to use float 28 as a default ABI because it's simple and it's supported by the hardware. And a lot of the symbols are due to past mistakes that we did, meaning we need to require to support for compatibility reasons. And there is more later why we need to do this and why this was a mistake. So this is a bit of archaeology in glibc implementations, and this is just to show how the library was involved and what we did that was not well designed, what we are trying to accomplish with this new implementation, and why it was done at the time and why we are changing now. So the first glibc that imported math library was 2.0 in 97. It imported this project that is used on other libc implementations. It's fdmlib. And there is a lot of code adaptations to work with double and log double back then. And it also means that this adaptation did not actually consider did not make a mathematical analysis of the accuracy. So it was not a direct translation between one implementation to the another. And there is a lot of issues regarding accuracy back then, but it was fixed over time. And we start to provide this SVAD error support that is still become a problem until today. So, and later on glibc 21, we added complex functions, which we improved over time as well. And on glibc 2.2, we start to adding more and more assembly optimizations for some architectures. The first one was x86 32-bit. And later we did for Intel AI64. And I'll say a bit more later. But on glibc 2.3, we've added another math library. This is the IBM accurated math library. And this idea of this library is to provide correct rounded implementations for the default rounded mode. And it did by adding, basically, for all implementations, a fast path with do operations with floating points. And if the floating point is not correctly rounded, after a test, it falls back to a multi-precision library that was really, really slow. but at least it provides correct rounded results. And Wilco here can give you a more well-thought answer, but it was really, really slow. And the main problem with this implementation is some inputs are really, really fast, but depending on the input, it can be like 50 times slower than the default one. But we keep this implementation for a long time, and we try to the first thing that we try to mitigate this issue is add this new finite math only support that was a GCC option that basically says that you're only operating with finite numbers, so it does not have infinite, not a number, or I think it's the normal as well. I'm not sure if it handles the normals. But the whole idea is you have new symbols on the libm that the compiler will call instead of the default ones. So you can have a bypass of some error handling. And it also was not well designed, and we end up moving to compact symbols on 230. And also glibc 215 starts to add ifunc variations or ifunc optimizations for some symbols. It starts with x86 because that's the architecture that has multiple architectures that it starts to provide instructions like FMA, new rounding modes that the maintainers back then thought it was a good idea to add new variations to improve performance. So we have on 2.16 a lot of conformance-ish fixes from Joseph. And there is some trigonometric assembly functions for x86. This is a bit important because this is a trend that started on this release where some architectures decided to, instead of provide a better algorithm for the generic implementation, they decided, let's tune using assembly only for one architecture because let's be clever, we don't want to move for generic implementation, let's just focus on a very specific architecture. And x86 did this initially, PowerPC followed on using the same algorithm on 225. So this starts to have a lot of different assembly implementations for the same math function, and it can become a problem. So 217, we added optimized multi-precision support. Basically, the multi-precision was done in generic manner, and then we started to optimize this with some assembly optimization, some compiler flags, because we start to realize that it was kind of slow on this fallback. And 232, we added the libm.h. The libm.h initially was based on an Intel library, so it was and it is currently a lot of assembly implementations that are very hard to maintain. I think someone has tried to clean this up, but it's really hard, and it's not clear how it was generated back then, if it was auto-generated from some C code, from some math library. But we keep this as is, and I think we extended it for AVX2 and AVX 512 sometime later. And glibc 224, we add some missing functions for some C standard extensions. And a bit more, and 236, we add float.h, 1.8 support on some architectures, x86 as an extension, and we add also this new type where long double is float.h. And on glibc 228, we start to optimize by removing code instead of adding new stuff, meaning we realize that the multi-precision implementation for some math functions are not providing a good performance and it's not really improving the implementation. And we start just remove the code support. I think we did this on the whole release. I think on 28 we removed all the code. There are some lingering files, but basically we don't have more this multi-precision internal library to support this. And 229 we imported another project from ARM, named ARM Optimized Routines. And the ARM Optimized Routines was a kind of different project because instead of doing ARM optimized routines for the ARM chips, what they did is to implement generic functions using C code that was targeting new CPU features. So the whole idea is we have a generic implementation that you can use as a generic implementation for the ARM library, and we try to optimize for ARM, but not only for ARM. So the whole idea is trying to come up with different algorithm strategies, new math ideas, instead of trying to optimize assembly by just fixing small bits. And it turned out to be faster than what we added for x86 and PowerPC. Go ahead.
Question on that particular topic. Right. As you were finding that these generic implementations that you got from ARM were as fast as or better than the handwritten assembly code for Power and x86 and had hopefully comparable accuracy, how much code were you able to remove of that handwritten assembly you guys had in place?
So back then, I think x86 added one symbol for scinf, another for cosf, and another one for sin and cosf, and another for x as well. So if I recall correctly, it's about 1,000 assembly line, one for x86, another one for PowerPC, and we could remove both of them.
That's fantastic. And I guess the follow-up to that would be, do you anticipate seeing that kind of cleanup happening again in the space?
Yeah, I have a very nice follow-up image to show you the improvements we have done.
I'm prepping the world for your next slides.
So this one, it seems unimportant, but it's very important, where we improve the usage of compiler built-ins internally. The whole idea is, let's avoid re-implement what the compiler provides us. And it's less art-specific code, less assembly code, less things to maintain. And with 234, we finish up the multi-precision code removal. Sorry. And on 238, we add that libmvec for ARM64. Again, different for x86. ARM uses try to leverage the compiler using C implementations instead of a whole block of assembly. And it's very interesting because you can see improvements over the GCC releases, and it also shows some GCC shortcomings that ARM is fixing. And like 1 year ago, we started to implement the new C23 symbols. And different from the previous version, we try to use using a template, which is not optimal, but at least allows us to implement the different float types at the same time. It's like a C++ template, but using C code and macros. And on 241, we start to implement, to import another project that's named CoreMath. CoreMath, it's a project from a professor in France. His whole idea is to implement correctly rounded implementations for all the functions. And what he did as innovation was he made some mathematical analysis of the requirement multi-precision support that we need to do, meaning we do not need to have a slow multi-precision library. We can emulate either using double-double or int28. And it ended up being a lot of faster than what we used to have on FDM-lib. And I'm going to show you what kind of improvements we have. And also we implement, optimize all other library functions. There, this ilogb, math.h. We implement also hypot with using a new algorithm. So there is constantly new improvements. So this boils down to these lessons learned. What we learned over this like 20 years of development, using different strategies to implement libm and optimize the library. The first thing, which is I think is the most important, is try to leverage the compiler instead of using assembly optimizations. For instance, the AR64 implementation that was also a very large assembly library that was imported from on glibc was never properly fixed on a lot of conformance issues. And once we removed the port, the library was away as well. And it means that if you add some assembly optimizations, it will generate a lot of maintenance. And you won't be able to keep all of them at the same properly maintenance. So that's the main problem we have here. Another thing is compiler will help you optimize some work that you not need to keep maintaining assembly code. And we have two examples here where the C implementations can be faster than what you initially think as a better option for optimizations. And another thing that leverage the compiler is it allows you to use new hardware features faster than have to create an assembly optimization for each new hardware generations that you have. So another thing is correctness without performance consideration will force clever solutions, meaning if you have a bad implementation or a not well-designed implementation initially, maintainers will try to come up with clever solutions to optimize bits of that implementation where they think they can. So we have x86 with ifunc support for multi-precision math library, a lot of clever solutions with some fast path, and end up with a whole assembly implementation that end up being slower than the generic, well-designed one.
Before you move on.
On the last bullet, you said, add architecture-specific routines to overcome bad design decisions for x86 and PowerPC. Can you give some color on what those bad design decisions were? And I'm assuming you're referring to a hardware design decision.
So what x86 and PowerPC end up doing is they take out the generic implementation we had for CNF.
Oh, okay.
They transform to assembly, optimize that assembly manually, and they push on the glibc, because either they could not get the same performance with the compiler or whatever, but they didn't actually change the mathematical usage on the implementation itself. So it's the same formula, manually optimized. And then when we come up with a new formula, a new mathematical way of doing the same thing, when you build for x86 and try to run the benchmarks we have internally, we found out that the new implementation was faster.
Got it, thank you.
Another thing that's beat us even now, it's bad designing error handling, because we still need, we still have support for this SVID, which it's like a standard global variable when you can define that kind of error you expect. And it still waits a lot of CPU time because we need wrappers for each math function. So it's sometimes a math function requires another function call. We cannot tail call some math calls. I'm still trying to remove this even now, but remove this requires new symbol. So it's not straightforward to do it. It requires some work internally. And one thing that, another thing that we found out, it's really hard to provide performance and conformance in a wide different hardware range. So I think the new implementations aims to focus on new hardware, meaning that we try to leverage new AAA 754 support that can be slow and on different hardwares, like the squared function, FMA, new rounding modes. So the decision that I did on the new implementation was, let's assume new hardware, and if the old hardware complains, let's see what we can do. But the idea is, let's optimize for what we have now. Another thing is that math and float port are really, really hard. It took like 20 years to have a new correct round implementations that faster, because there is new development in the math, and I'm not a mathematician myself, but I saw that there's a lot of papers trying to analyze the error handling, how the math operations produce, what kind of error you expect, and each trigonometric or exponential function requires a different analysis. So it's a lot of work to come up with new algorithms to have correct rounded or better implementations. And we have, so this is the recent efforts that we have on glibc. So as far as I know, the glibc, the math library with the largest coverage for the new C plus C23 functions. We have all the new logarithms, all the new exponential functions, all the new trigonometric ones, and also the new mask functions like power R, power N. Joseph as well added the support for the TSX extensions, which is new classified functions, conversion from different types, magnitude handling. So there's a lot of new symbols and all new implementations. And now we fixed more than 200 bugs in this last 10 years. So this is a subtopic that is really important, is how to integrate and why we are integrating different projects on the LibM and not just keeping what we have. So the first one is the ARM optimized routine, and it shows a lot of, it adds a lot of implementations for different symbols. And it was well crafted, target new hardwares, and showed that it was faster than what we used to have, using C implementations for a wide kind of different hardwares. It has some trade-offs between accuracy and performance, but I did some accuracy checks, and it was really, really good. It was not correctly rounded, but it was really, really good. So there is a more on. The question is how we should balance between these two. And Core Math also provides high performance, but since it aims to do correct rounding, the problem is to do correct round, it requires you to do more operations and more checks. You need to do a different strategy. You need to do some multi-precision work to do the correct round phase. So it's a trade-off that we are still discussing on the mail list if we should do or not. And but at least both libraries are easy to integrate on different projects. So are quite isolated, so we can do symbol by symbol. So this is the performance improvement we have so far. The first one is on ARM64 using a new verse 1. I didn't add I forgot to add the configure options I use on glibc, but it's the usual one a distribution is going to use. It's enable fortify, enable stack handle strong, and using O2 without any flags or any special flags. And it compares what we have on glibc 235 to 243 using our own benchmarks. So no standard benchmarks. If you using glibc, you can make bench, and you have the programs that I use to get this number. So you can see that some symbols like TGMF, it's a large improvement. In general, we have a 68% of improvement in geometric mean, and it's the same for x86 using a Zen 3 chip, which is a new chip that I have access. And for this one, I did a slight different build. I use x86 version 3 as a default ABI because that's the one that provides FMA and other instructions. Otherwise, I had to rely on some internal routing through ifunct. And this is what new distributions I'm aiming for. So I think it's a real comparison that we might have recently. And now we have a 50% geometric mean improvement in this, I believe, 10 release, 8 releases. So this is the part that I don't actually have straight answers. Oh, go ahead.
It was in Zen 3, I understand, but did you try in an emission on for AVX 512?
No, so the thing is, most of this implementation does not use vectorized instructions. What we are getting for the x86 version 3 here is instructions like FMA, square root, new routing modes. We do have the libmvec. Go ahead, Fran. So
you also get the non-destructive destination support. So it's fewer instructions executed because of the VEX encoding.
But I think the AVX, the new AVX, will show its strength in more vectorized code. We do have some libmvec support for AVX, but we don't have benchmarks on glibc itself to track these improvements that we have over the years. I think Intel has some blogs about what kind of improvements you're going to expect from the libmvec.
I think that we have FMA from the get-go. I don't think we'll see as big of a gains as they've seen, but I am very encouraged by the integration of the ARM floating point libraries, because anything that gives us a generic implementation that produces better code than handwritten assembly, that's really good. So I'm encouraged. I think we ought to run this and do some testing for this.
There's another thing.
One thing, supplemental question. Did you try? It's okay.
He's going to project.
Did you try compiling the generic?
It's for the recording.
Oh.
Yeah, that way people can.
Did you try compiling the generic code, which I assume the non-intrinsic code, on an x86 machine? So you told we have generic code which were brought in for ARM processes, right? So I assume x86 code is written through hand assembly code?
Yeah. No, I did on this one here. Yeah, when we added the ARM optimized routines here, we found out that x86 code was slower. So we removed them.
You told it is for selected routines, not for all routines, right?
No, it's just for the routines that x86 overwrite.
Okay.
So x86 don't overwrite all the routines. It's just a bit of them
I understand, yeah.
to override, and we found out that it was wasted resources doing wrong, slower code. This is an open question, which is another thing that I forgot to add, which is important, is these implementations, all of these new implementations that we have here on the float is faster and correctly rounded. So it means that it's not only faster, but it has better accuracy. And it was really improvement over time. So what might happen in the future? So we still have a lot of bugs open. Most of them are easy, meaning missing RNO, missing some error handling, but some symbols are not showing accuracy. And that's the hard part, because it will probably require someone with mathematical background to come up with a better solution. And it's really hard because it's some symbols that are really complex. I think it's JN0, JN1, which is a Bessel mathematical function, which is really complex. It's not easy to implement properly. We need to remove the SVID error handling. It needs to go, it's slower. It does not add anything. And on some patch set I sent recently, it improves performance throughput to to 15% on some symbols. So I think that's something that we need to focus and get rid this at all. I think I plan to continue to work on integrated core math implementations. Now for the double ones. The double ones are kind of slightly different from the float because some of them require some multi-precision support. But different from the previous IBM support, it requires less multi-precision bits because the mathematical development specified that it was not required up to 1,000 bits. Only it's between 128 to 200 bits of precision, which is way less. And some performance-wise, some symbols show better performance. Some small regressions are neglectable, but on some symbols we do see a lot of regressions. But at the same time, these symbols that I focused initially was the one that we have the worst accuracy on glibc. So I think for this initial phase, it's more like a discussion. What should we focus? Should we trying to integrate new projects with correct round implementations and evaluate if it's worth or not? Or should you keep using generic implementations that are more stable or show better performance? Which is another question I have, which is, should we do performance over accuracy? Meaning it simplifies implementations. There is no need to use this strategy that is used on a lot of correct round implementations, which we have a fast path, a rounding test, and an accurate path. And this accurate path is really, really slow sometimes. Another thing that I would like to ask you is what kind of expected accuracy should we focus on? On glibc, math tests we trigger regressions only for 9 ULPs, but depending on how you use this is really, really large. So it really depends on what the users expect us to provide. And another thing is, should we focus only on the default rounding mode, or should we use all the defined rounding modes that the floating point supports? And another thing is which kind of hardware should we support? And because we still support ABIs from like 20 years, 25 years ago, and new chips are different. It supports more stuff, and trying to emulate this instructions, for instance, trying to emulate FMA is really, really slow, even on x86. So that's another question I have. Or should we focus on accuracy over performance? Correct rounding is really consistent, meaning if you have a correct round implementation, you can expect the same output independently of the hardware you're running or the ABI you're running. So this is it really depends on what the user expects. It also helps with numerical stability. Some numeric algorithms expect correct rounding, and if we provide this, it's one less source of problems that user will need to debug. And another thing that I think is quite important is we have outputs independent of the ABI in library versions, meaning independent of the library the version you're gonna use, you're gonna have the same result if it's a correct rounding. Because back then we used to have some internal testing to check what's the expected accuracy for each symbol, and we document this on the manual. But the problem is it was a heuristic check, meaning we come up with some numbers, some inputs, we calculate the results, and we try to do a best effort of the expected results, but it was not the real expected accuracy for the symbols. It's like a best effort because it's really, really hard to come up with all the ranges, especially on the binary 64 or float 128. So we end up to remove this because it was a source of extra maintenance because you need to run on each architecture, on each ABI to check what's the expected result. And some actual maintainers end up not doing this, and we had to update this later. So it's not easy. On this accuracy over performance, we still have a new recent advance in floating point arithmetic that show that correct round can be performant. And the slow path can be implemented using this double-double arithmetic, which is the same strategy the IBM uses for its long double on some ABI. And the new math advances, it's mainly to define what kind of error you're going to expect for this double-double arithmetic. So if you're doing multiplications, what kind of error you're going to, and you use with the defined error, you can tune how you're going to implement this on the slow path. So you do not, sometimes you do not need a multi-precision library to do the slow path. You can do using double-double, and there is other techniques to achieve high precision as well. So Paul Zimmerman has some works to formalize better the errors, and the required bounds and multi-precision libraries for the algorithm to transform with overfloating type. So it's a constant work on how to tune these implementations, and this come up with the core math library that I'm trying to integrate. And I think another strategy is we also can have both. If we design the library to do this, meaning we can have either new implementations, which are correct rounding, but with new symbols, and we keep the old one, but the new one we provide as a new interface. I'm not very fond of this because it generates extra maintenance, and which implementations are required more testing, more work. So, but it can be a way to provide both of them. Another one is we only provide the fast, not correct round implementations as with fast math. Since the user expects not accurate implementation, we can leverage this way to use new symbols. So, and libmvec follows this idea. libmvec shows has a higher bound of error for this internal implementations using different strategies. And I think to have a better idea, also we need new benchmarks, more data points, because the only one that we have so far is synthetic ones, either come up with traces from real workloads, but it's only a small part of the benchmarks we have. The rest of them is like, let's define a range and generate random numbers and see how it plays. But it will be good to see from the users what kind of range do you expect for the symbols you're going to use. And this is the part that I don't have straight answers. It would be good to have some feedback. Should we keep supporting C23? And what kind of optimizations do we want to add on these new symbols? Because some new symbols are quite complex, like compound N. And we only use very crude, not I would say crude, but very direct implementation that it could be optimized. And another thing that I have is, should you care about code size? Is it something that people will?
I might have a biased opinion here, but no. I think it's less and less important over time. You know, I don't want to say it doesn't matter at all, but it matters, at least over the last 20 years, I see it mattering less and less every year. So.
All right.
Size of data types can still matter though.
Yeah.
It can, you know, it's,
So
that's why I don't want to be absolute on it.
Yeah.
But I certainly wouldn't prioritize code size.
There's some concerns about large data tables in the megabyte range for some things. We probably wouldn't want to do that for things like decimal floating point.
So one thing that these new corrected round implementations do is some implementations require a very large table. because you have this fast path which is like a polynomial approximation, but if the polynomial approximation does not give you the answer, it falls back to a large multi-precision work, and this requires even large polynomials, large tables. So that's a question, because it generates more that data cache pressure. So that's really, and that's why it would be good to have better benchmarks to see, is it become a problem? It's not become a problem. So
Totally agree. And maybe, one more nugget there. I think maybe this turns into distinguishing between code size and data size.
Yeah.
So data size, I would say, is probably going to continue to have some relevancy, while code size probably will continue to decrease in relevancy.
Yeah.
So if you're building big tables, that's probably a bad idea. If you're having another blob of code in there, yeah, don't really care.
No.
So that's the refinement I guess I would make.
Okay. Another thing is, should we add more ifunc support on glibc? It's really, really important on x86 now, but even for x86, they are moving to build everything as x86 version 3 is default. So should we remove ifunc? Should keep ifunc? It's I don't know. I expect that RISC-V will probably start doing this as well. I don't know, but the main problem with ifunc, it requires a lot of internal plumbing, and it can be really tedious sometimes. A lot of work, a lot of files to keep track of, but it's an option.
Yeah, I think you mentioned RISC-V and ifuncs. I don't think we'll use a lot in the floating point library. I just don't see the architecture needing it yet. I haven't seen the extensions that would really benefit utilizing ifuncs. So I wouldn't worry a lot about it at this point.
Another possible project is, should we try to consolidate libmvec? By consolidation, I mean try to come up with a generic framework and build the implementation on top of the generic framework, so we can have a consistent ABI for our architectures. Because right now, x86 and ARM64 are implemented independently. It's not bad, but it requires more work from GCC. A new implementation for RISC-V will ask, should follow x86, should we follow ARM? What kind of ABI should we expect? And we have an example with this Leaf, which is a project that aims for this direction. I recall that I chat with some ARM64 developer and says that Leaf, it's a nice framework, but it does not provide all the performance that we expect for a very direct implementation. So that's an open question. I don't know. Just maybe start to doing some symbols and see how it plays. So that's one option. Another thing that come up from time to time is, should we add decimal floating point support? It's a whole new library. As Florian said, it sometimes requires large tables. Not sure about its usefulness. Only a couple of hardwares do provide instructions for that, PowerPC and 639. And this is an open question. Joseph Myers has laid out the required work that we expect to do. It's a lot of work that to integrate DFP. So this is our open question. Another thing is, another possible project is adding the C++17 special format functions. There are, I think it's 21 new functions that C++ implemented itself on its header, so it might be an option to implement on libm as an optimization. I don't know. I'm not sure how it's going to be used, or if C consumers are going to expect such functions. Another thing is, should add more extensive math testing on libm, because right now we only run predefined tests. It would be good to have a way to let's run thousands, billions of tests but it will consume a lot of CPU time. So that's the, and other project does. Core Math has a way to, it uses OpenMP to run a lot of tests in different cores to check the results. So that might be an option to add on glibc as an external test that is not run by default. Another question I have, should we add float.16? There's a open bug report to track this, and this is also a lot of work. Not sure if all the ABIs will be willing to add such support, but at least we can initially base on the float 32. So this is I don't have a answer for that. And another question is, should we improve for soft float and old chips? There are some old implementations that are really, really slow. For instance, FMA for the generic implementation is quite slow because it requires changing the round mode. So on the old chips, it stalls the FPU. And it's really bad. It will be better to implement as using integer operations. So that's another question, but it's not easy. It requires some time to implement this new work. So that's another question I have. Do we care about that? I don't know. And that's it. Thank you. Any questions?
I think the float 16 is interesting, but I don't know what to do about it. I don't know how much to invest or what we would do. But I do think it's something we probably need to talk about more and think about if there is anything we would or wouldn't do. And to some degree, I'm nervous about the maturity of bfloat versus float versus something that's IEEE compliant versus something that is hardware dependent, because the hardware vendors care about speed, especially if float 16 is being used for like neural network math or other things, and they really don't care about correct rounding or anything in float 16. If you do anything to impact performance, then it's a loss, right? But then at the same time, that means or yields that some inference models just produce different results wherever you run them, right? But we might actually care fundamentally at the software layer. Well, what if we actually had a float 16 that was consistent and produced the same answers every time you did those computations? But then again,
the industry's going though.
Correct. And if the industry doesn't go that way, then no one's going to use them. And so then again, I don't know what to do in the float 16 case, but I like that you raised it because it's an interesting topic.
I wonder if on the float 16 case if on the float 16 case you just defer for a little while longer and see if there's some consolidation in terms of direction.
I agree, and I think there's probably other libraries that are using float 16 or will be the place where that like testing it out and experimenting will happen, and then we'll have to look at what falls out of that or what shakes out of that.
If the iFunc support to get old chips to decent performance is a maintenance burden, we could encourage distributions to build a variant it's a different direction. So if distributions want to maintain compatibility with old chips and then they get the bad performance from the missing FMA support, and we currently add the iFunc variants that use FMA to deal with that. But we could also say, okay, we move that code and tell distributions if they want to have that kind of compatibility, you have to build a x86-64v3 libm and ship that as a variant library that gets loaded automatically on your systems.
Yeah.
That could reduce our maintenance burden.
Because it come up with the question about code size, because if I recall correctly, iFunc on x86 about 40% of the libm size for the extra implementations.
But yeah, I mean, I think at a certain point we need to optimize for maintainability on our side.
Yeah.
Yeah, I like the idea of building separate libm's for different settings, and then you just load the one that you want, and that doesn't cost you code size at that point. You only load one.
Is that? Okay, thank you.
Thank you again.